Good afternoon, class. We will now begin chapter 11, the last chapter before exam 5. Now I'm going to combine sections 11.1 and 11.2 into a single video because they're very similar. Now looking at our exam 5 formula sheet, the two formulas at the top in the right-hand column are our sections 11.1 and 11.2 formulas. And they look very similar. The only difference is that one is a z-value where sigmas are known, and the other is a t-value where the sigmas are unknown. So just as we have discussed creating a confidence interval for a single population parameter in chapter 8, and then extended that process to creating a confidence interval to compare two population parameters in chapter 9, we will extend the hypothesis testing procedure that we learned in chapter 10 so it is possible to test claims involving two or more populations. The steps will be the same as we saw in chapter 10. Step 1, state the hypotheses. Step 2, calculate our boundary value. Step 3, determine the decision rule. And step 4, we want to conclude. The difference in performing a hypothesis test involving two populations versus one population comes in steps 1 and 2. In steps 3 and 4, the rejection regions and conclusions are the same as if we were testing a single population. When testing two population parameters, we can state H0 and HA in two different ways, though algebraically they are equivalent. Forms for testing two population means. And again, we're going to denote the two population means as mu1 and mu2. So they're going to give you a group in the problem first, and we'll call this population 1. And population 1 has a mean mu1. And then they will mention another group of individuals, and this will be dealing with population 2. And population 2 will have a mean mu2. Now, for a left-tailed test, we have two methods. Our null hypothesis is always going to consist of equality. Notice that for each test, left-tailed, right-tailed, and two-tailed, our null hypothesis is always that the two mu's are equal. Using algebraic properties of equality, if I subtract mu2 from each side of the equality, I get the statement mu1 minus mu2 equals 0. So these are equivalent. So either we write it like this, where the mu's are equal, or we move the mu2 to the other side by subtracting, and we write it as a difference. And this is what we're going to be interested in, the difference in means. And this is what we saw in chapter 9. Now, our alternative hypothesis, we still always use the three symbols we saw in the previous chapter: less than, greater than, or not equal to. Remember, less than points to the left. It's a left-tailed test. Greater than points to the right. It's a right-tailed test. And the not equal symbol represents our two-tailed test. So either the first mean is smaller than the second mean, the first mean is bigger than the second mean, or the first mean is not equal to the second mean. And again, using similar properties of equality, subtracting mu2 from each side, we get the following three statements. In general, it is not always the case that we write mu1 equals mu2. In other words, mu1 minus mu2 equals 0 for the null hypothesis. However, for the sake of simplifying things a little bit in our class, this will always be the case. Now, there are other problems where these are not equal. There's a variation of that. We're not going to get into that. So for the sake of our class, our null hypothesis will always assume that the mean of population 1 equals the mean of population 2. Again, for the purpose of our class, just as we saw in chapter 9, we will assume that the two samples given in each problem are independent. And you can review what that means going back to chapter 9. That is, data from the first sample are not connected to the data from the second sample. Our two test statistics, so we break them down into two categories: if sigma is known and if sigma is unknown. Now again, we're dealing with two populations, so really we have two sigmas, a sigma 1 and a sigma 2. So if sigma 1 and sigma 2 are both known, we're going to use our z test statistic. And notice on our exam 5 formula sheet, the formula has sigma 1 and sigma 2, meaning we know the values for sigma 1 and sigma 2. If sigma is unknown, we're going to use our t-test statistic. And looking at our exam formula sheet, this is the formula where we replace sigma 1 and sigma 2 with our sample standard deviation, S1 and S2. There is a t-test statistic formula when sigma is unknown and the population variances are assumed to be equal, given by the following. However, for our class, we will not deal with this scenario, okay? So there's really two scenarios where the population variances are assumed to be equal and the population variances are assumed to be unequal. This is the nastier formula. We're going to delete this scenario for this class. Again, for the sake of simplifying our criteria for this chapter. Let's look at an example. So a university researcher is interested in a new instructional method of English for university freshmen whose scores require them to complete remedial work. He is comparing the traditional 2-semester instruction against the new 1-semester co-requisite instruction. He wants to test the claim that students who are in the traditional English remediation sequence score lower on the departmental final exam in English Composition 1 than their counterparts in the new single-semester co-requisite English class. 93 randomly selected students were chosen for the study. Of this group, 41 students were randomly chosen from the group who took the traditional remediation English classes. This group scored a mean of 66.47 on the departmental final exam. The other 52 students were randomly chosen from the new 1-semester co-requisite English classes and scored a mean of 69.43 on the final exam. Assume that the population standard deviation for students in the traditional English class is, assume that the population standard deviation for the students in the traditional English class is known to be 8.05, and the population standard deviation for students in the new co-requisite English class is known to be 9.22. Test the claim using a 0.10 level of significance. Now, again, because we're dealing with two populations here, the problems are going to become a lot longer. So, I have a posted solution here written out. These problems become a bit longer. I have some problems that I work out in the homework example videos where I not only solve them, but I talk through them as well. So please go through this solution, this written solution posted below the video on this page. And also, if you're still confused, please watch the homework video first for section 11.1 and 11.2. And if you're still confused after reading the solution and watching the videos, please post in our Chapter 11 discussion board or reach out to me via my UNA email. Now, another example that we can work, a manufacturer fills soda bottles. Periodically, the company tests to see if there is a difference between the mean amounts of soda put in bottles of regular cola and diet cola. A random sample of 14 bottles of regular cola has a mean of 501.6 milliliters of soda with a standard deviation of 3.9 milliliters. A random sample of 16 bottles of Diet Cola has a mean of 498.9 milliliters of soda with a standard deviation of 5.3 milliliters. Test the claim that there is a difference between the mean fill levels for the two types of soda using a 0.01 level of significance. Assume that the population variances are not equal since different machines are used to fill bottles of regular cola and Diet Cola. Okay, so again, these problems become a little more in depth and it will make this video a bit longer, which isn't bad, but I have the written solutions below this video posted on this page. Please walk yourself through those. It's the same 4-step process, only steps 1 and 2 change, okay? So try to follow along with those solutions. If you're still confused, please work through the section 11.1 and 11.2 homework videos that I have posted in this module. And if you're still confused after that, please reach out to me via our Canvas discussion board or my email.